In this video, we are continuing our study of propositional logic. So first, consider two propositions generated by P and Q. Not P and Q, and not P or not Q. At first glance, they are different. In form, they are different, but it turns out that they have the same meaning. So one way to see this is to substitute actual propositions for P and Q. So here's an example. Let's let P be, I've been to Toronto, and let's let Q be, I've been to Chicago. Then the first one, not P and Q, translates to, I haven't been to both Toronto and Chicago, while the second one, not P or not Q, is, I haven't been to Toronto or I haven't been to Chicago. So clearly we can understand that these have the same meaning. We can also create the truth tables, and we know that because we're involving two propositions, P and Q, our truth table is going to have 4 lines, as you can see here. And in all 4 cases, these will have the same truth values. So we have the case where P is false, Q is false, then the first one is true, the second one is true. If P is false but Q is true, then again, the first column is true, the second one is true. If P is true, Q is false, then we have true and true. And if P is true, Q is true, then these 2 columns are both false. So these are equivalent logical expressions. Now we'll introduce a very important concept, and that is the concept of tautology, and then we'll introduce contradiction. An expression involving logical variables that is true in all cases is called a tautology. So a logical expression that is always true is called a tautology. And here are some examples. So the one that we just looked at, we saw that their truth values are always the same. And that means that if we had the biconditional connecting them, the truth table for that would be true if and only if true, that's true. True if and only if true, that's true. True if and only if true, that's true. Or false if and only if false, and that's also true. So the truth table here would be, the column would be 1, 1, 1, 1, or true, 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 and that's what we call a tautology. Another example would be P or not P, and we've seen this in our previous lecture note, but let's just take a quick look one more time at the truth table for P or not P. So if we let P be true or false, then not P is going to be false or true. P or not P, I just need one true in order for it to be true. So in the first row, I get true from P, so I say that P or not P is true. In the second row, I get the true from not P, so I say P or not P is true. And when we see this column in a truth table where all of the entries are true, this is called tautology. And this will be denoted with a capital T, or perhaps the number 1. And there are some more examples here. P or Q implies P, Q implies P or Q, P or Q if and only if Q or P. These are all tautologies. We'll also have the idea of a contradiction, which will be a logical expression such that for all cases it's false. Then we'll call this a contradiction, and we'll denote it with either capital F or perhaps 0. Or you may also see script C like that. A cursive C is contradiction, or a capital F. Some examples of contradictions would be P and not P, or P or Q and not P and not Q. Let's look at P and not P. We can add one more column to our truth table here. What if we did P and not P? So now, because we have the conjunction and, we would need both places to be true in order to claim that it's true. But of course, P and not P are always going to have opposite truth values. So true and false is false. False and true is false. So this is always false. That's contradiction. Now we already sort of understand the idea of equivalence, but we have the definition here in a formal way. Let S be a set of propositions and let R and S be propositions generated by S. R and S are equivalent if and only if the biconditional R if and only if S is a tautology. If that's the case, then we'll change this single arrow to the double arrow. Just like in algebra, there are more than one way of writing an algebraic expression. In logic, we'll have often more than one way of writing a logical expression that has the exact same meaning or the exact same truth values. So here are some equivalences. P and Q, or not P and Q, if and only if Q. P or Q, if and only if Q or P. And I want to point out here that all tautologies will be equivalent to each other, and all contradictions are equivalent to each other. Because to be an equivalent, we need to have the same truth values. We know that anything that's a tautology, all of the truth values are true, so any tautology will be equivalent to any other one. And similarly, anything that's a contradiction will have all the truth values equal to 0, so any contradiction is equivalent to any other contradiction. Okay, let's see an interesting example that's going to help us introduce the idea of implication. So consider the two propositions. The money is behind door A, and the money is behind door A or door B. So imagine that we're told that there's a large sum of money between one of two doors, marked A and B, and that one of the two propositions here is true and the other is false. That should be enough information for us to know which door the money is behind. So all that we need to realize is that if X is true, if the money is behind door A, then Y is true, because Y simply says the money is behind door A or door B. That means that we must have that X is false, then Y can still be true, and we can conclude that the money must be behind door B. So this is an example of a situation in which the truth of one proposition leads to the truth of another. Y can be true when X is false, but X cannot be true when Y is false. In this case, we say X implies Y. Let S be a set of propositions and let R and S be propositions generated by capital S. We say that R implies S if R single arrow S is a tautology. And then we're going to upgrade the single arrow to the double arrow when that's true. A commonly used implication is called disjunctive addition, and that will be P implies P or Q. And that's verified by the truth table up here. So we can see we have our column for P, our column for Q, and our column for P or Q. Now, if we want to verify P implies P or Q as a tautology, we can just simply check P implies P or Q. So we'll have false implies false, that's true. False implies true, that's true. True implies true is true. True implies true is true. So we can see that P implies P or Q is a tautology, so we can go ahead and upgrade that to the double arrow. And this implication is called the disjunctive addition. It's often used, so we go ahead and make special note of it here. One other thing to note is that in the last lecture note, when we defined the proposition generated by a set, we made a note at the time that we didn't include conditional and biconditional operators because we'd be able to state them in equivalent form using just negation, conjunction, and disjunction. And so that is because of these equivalences. So the conditional P, if P then Q, is equivalent to not P or Q. So this is very important. I'm going to go ahead and circle it. And the biconditional P if and only if Q is equivalent to P and Q or not P and not Q. So I'm circling these because we're going to want to remember these. These are going to be tools that we can carry around in our toolbox and use them as it is convenient. So let's work through some exercises together. First, we're given a list of compound propositions, and we're asked which are equivalent to one another. So the simplest way to get started with this is going to be to just make truth tables for them, and then we'll compare which columns in our truth table have the same values and conclude which are equivalent. So I'm going to start with P, Q, and R. And we know because we have 3 propositions to start with, we're going to have 8 rows in our truth table. So for P, I'm going to do true, 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 and then false, 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 false. For Q, true, true, false, false, and then true, true, false, false. And for R, I'm going to alternate every other one, true, false, true, false, true, false, true, and false. And then I'm going to start collecting the pieces that I need. So for the first one, A, I have P and R, or Q. So I'm going to make a column for P and R. And then I'm going to use the columns for P and R and find these truth values. So I need both of them to be true in order to say that it's true. So I have true, false, true, false, 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 and false. So now I can make this compound statement P and R or Q. So now I'm looking at this column and this column, and I just need one true in order to claim that it's true. So here I'll be true, then true, true, false, true, true, false, and false. So that's A. I'm just going to sort of keep it on the back burner so that I know once I finish my truth table, we're going to compare and see what's equivalent to what. So for B, it looks like I'm going to need a column for R or Q. So I'll go ahead and make R or Q. And now I'm looking at these two columns. And I just need one true to say true. So I've got true, then true, true, false, true, 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 false. And now I'm ready to do P or R or Q. So I'll be looking at P and R or Q. So I have true, 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 and then it looks like I have true, 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 and false. And that's B. For C, I need R and P. R and P is the same as P and R, which I already have here in my table. So this is also R and P. Then I have not R or P. So I can make a column for not R. Then I'm looking at my column for R, and I'm just going to make these the opposite. So not R should be false, true, false, true, false, true, false, true. Then not R or P I'll look at P and I'll look at not R. Since I have disjunction, or I'm just looking for one truth in order to say that it's true. So I have true, 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 true. Then I'll have false, true, false, true. Letter E, so let me go ahead and make note, this is D and this is C. Letter E, I need P or Q and R or Q. I already have R or Q here, so let's do P or Q. Then I'm looking at these two columns. I'm going to have true, 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 and then I'll have true, true, false, false. So then I can make letter E, P or Q and R or Q. P or Q and R or Q. And so I'll be looking at R or Q. I'll be looking at P or Q. So first I have true and true, then true and true, then true and true. So the first three are true. Next I have false and true is false. Then I have true and true, true and true. The last two rows are true and false, false and false. So these are false and false respectively. And that is E. F is R implies P. So I can just use the columns for R and P. So looking here at R and here at P. R implies P. So I have in the first row, true implies true, that's true. False implies true, that's true. True implies true is true. False implies true is true. True implies false is false. False implies false is true. True implies false is false. And false implies true is true. Letter G is R or not P. So I can make a column for not P. And that's going to be false, 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 true, 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 true. Then I want to do R or not P. So then I'm looking at R or not P. So I'm going to have first true, then false, then true, then false, then true, 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 true. And that's my letter G. And finally, letter H is P implies R. So I'll be looking here at P and R. So the first row is true implies true, that's true. Second row, true implies false is false. True implies true is true. True implies false is false. And then I have false implies true, that's true. False implies false, that's true. False implies true, that's true. False implies false, that's true. Alright, so now I've completed my truth table, and I just need to compare, when I look at A, B, C, D, E, F, G, and H, which are equivalent to which. So let's look at A, which was P and R, or Q. I have true, 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 false, true, true, false, false. That looks like that should be equivalent to letter E. So true, 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 false, true, true, false, false. These are the same. So I'm going to say A and E are equivalent. And we use this symbol for equivalence. Now what about B? True, 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 false. Everything true except the last one. It doesn't look like I have anything equivalent to B. And I also don't see anything equivalent to C, which is true, false, true, and then everything else false. But if I look at D, which was not R or P, then I have true, 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 false, true, false, true. And that appears to be equivalent to F. True, 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 false, true, false, true. So I get to say D is equivalent to F. And then looking at G, G and H are equivalent. They have the exact same lines in their truth tables. True, false, true, false, true, 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 true. So G is equivalent to H. Now let's look at these expressions. So A and E are P and R or Q. That's equivalent to P or Q and R or Q. So this is the distribution of the disjunction or over the conjunction and. You can see I have P or Q and R or Q. And that's exactly what I have there in E. So that's always going to be logically equivalent. Then D and F are logically equivalent. This is the one we discussed earlier. R implies P is going to be logically equivalent to not R or P. So this again is going to be a handy equivalence to remember and use whenever we need it. And then in the same fashion, P implies R is equivalent to R or not P. All right. Let's look at the next example. In the next example, we're asked to construct a truth table for P and not Q, or R and P. So as before, I'm going to start with P, Q, and R, the first three columns. And we know we're going to have 8 rows in our truth table. And we're going to start with P is true, 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 false, 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 false. Q as true, true, false, false. Then true, true, false, false. And R we're going to alternate true, false, true, false, true, false, true, false. And I'm going to do this piece by piece. So I need not Q. That's going to be false, false, true, true, false, false, true, true. Then I need P and not Q. So looking at P and not Q, I'm going to have true and false is false, true and false is false, true and true is true, true and true is true, false and false is false, false and false is false, false and true is false, false and true is false. Next I need R and P. So looking at columns for R and P, I have true and true is true, true and false is false, true and true is true, true and false is false, false and true is false, false and false is false, false and true is false, false and false is false. And now I'm ready to put them together. I'm going to be looking at P and not Q, or R and P. So looking at these two columns, and since it's or, I'm looking for only one truth value. So false and true is true. False and false is false. True and true is true. True and false is true. False and false, false. False and false, false. False and false, false. False and false is false. So I have true, false, true, true, false, 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 false. So that's part A. Then part B says, give an example other than X itself of a proposition generated by P, Q, and R that is equivalent to X. So one thing that I notice is this looks sort of similar to what we did in exercise 1, where we saw that A and E were equivalent because I had the distribution of the disjunction over the conjunction. So here I have P and not Q, or P and R. So I think that if I write this as P and R or not Q, that might be equivalent. So let's investigate that. Let's start by writing R or not Q. I already have a column for R and I have a column for not Q. So R or not Q will be true, then false, then true, then true. Then it looks like it's true, false, true, true. Now let's do P and R or not Q. So now I'm looking at P and R or not Q. I need both values to be true. So it looks like I should have true, false, true, true. Then false, 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 false. Now let's compare. I wanted something equivalent to true, false, true, true, false, 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 false. And I have true, false, true, true, false, 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 false. So these are logically equivalent. And how did I know that this should be correct? Because I saw the pattern and I saw that this looks like the distribution of this conjunction over this disjunction. Just like in the previous problem. So that's part B. Then part C, give an example of a proposition other than X that implies X. Give an example of a proposition other than X that is implied by X. I'm going to actually save these exercises and we're going to come back to them after we do one of the future exercises. Question 3 says, is an implication equivalent to its converse? Verify your answer using a truth table. So let's say we have two propositions, P and Q. And using the truth table, we want to determine if the implication, P implies Q, is equivalent to the converse. The converse, remember, would be Q implies P. So P can be true, true, false, false, and Q true, false, true, false. Then P implies Q will be true implies true, that's true. True implies false is false. False implies true is true. False implies false is true. What about going the other direction? Q implies P would be true implies true, that's true. False implies true is true. True implies false is false. True implies false, false implies false is true. And immediately we can see that these are not equivalent because these rows don't match. So an implication is not equivalent to its converse. Now in the last video we saw a specific example of one case where it does happen. That would be if two statements have the relationship of being if and only if, then this will happen. But in general, we don't want to make the mistake of assuming that an implication is equivalent to its converse. It's a very common mistake, but we're not going to make that mistake. Now, suppose that X is a proposition generated by P, Q, and R that is equivalent to P and not Q. Write out the truth table for X. So because X is going to be generated by P, Q, and R, I know I'm going to start a truth table with 3 propositions, so I'll have 8 rows, P, Q, R, and as always, we'll do true, 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 false, 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 false for P, then true, true, false, false, true, true, false, false for Q, and true, false, true, false, true, false, true, false for R. And all I know is that I want X to be equivalent to P or not Q. That means I want it to have the same logical values. So let me find the truth table for P or not Q. First, I'll find not Q. That's false, false, true, true, false, false, true, true. Then P or not Q. True or false, true. True or false is true. True or true is true. True or true is true. False or false is false. False or false is false. False or true is true. False or true is true. Then I don't know what the proposition X will be. I just know that its truth values should be true, 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 false, false, true, true. Because in order to say that it is equivalent to P or not Q, it should have exactly the same truth values. Question 5. How large is the largest set of propositions generated by P and Q with the property that no 2 elements are equivalent? So I can think again about the truth table, and I'm thinking of propositions generated by 2 elements. So I know that this truth table is going to have 4 rows. In order for no 2 elements to be equivalent, that means that none of the columns can match. So I have 4 rows. The question basically boils down to how many different ways can I fill in 4 rows with true and false so that none of them are the same. So in my first row, I have 2 choices. I have true or false. In my second row, I have 2 choices, true or false. The third row, true or false, 2 choices. And the fourth row, true or false, 2 choices. So it's going to turn out that there are going to be, we're going to use multiplication. And there will be 2 times 2 times 2 times 2. Equals 16 different propositions. (16) is the largest possibility to make sure that I have different truth values in the table. Question 6. Find a proposition that is equivalent to P or Q and uses only conjunction and negation. So again, I'm going to start with a truth table to try to solve this question. I know that I'll have for P true, true, false, false, and for Q true, false, true, false. Since I'm told that I can only use conjunction and negation, I'm going to go ahead and put not P and not Q in my table. So not P is false, false, true, true, and not Q is false, true, false, true. I also want to see P or Q because that's the thing I'm trying to be logically equivalent to. P or Q is true, 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 false. So I'm looking for something that is true, 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 false. So what happens if I do not P and not Q? Because I'm told I can only use negation and conjunction. So let's see, not P and not Q. That is false and false is false. False and true is false. True and false is false. True and true is true. So I want something that's logically equivalent to true, 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 false. And what I see that I've created is false, 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 true. So these are exactly opposite. I'm told I'm only allowed to use negation and conjunction. So let's do negation of, negation P, and negation Q. I need these parentheses so that it's clear that I'm negating this entire compound proposition. So this will be true, 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 and false. And there we can see that they match. So what we found out is that P or Q is logically equivalent to negation of, negation P and negation Q. Now here's the question that's going to help us go back and answer question 2, the second half. So it says, explain why a contradiction implies any proposition and any proposition implies a tautology. So let's think about this. What did we learn about contradiction? Well, a contradiction is always false. A contradiction is always false. Or, in other words, if we have a contradiction in our truth table, its entire column will be capital F, capital F, capital F. And we know that false implying true is true, and false implying false is true. So if we have a contradiction and all of its truth values are false, then a contradiction implying any proposition will be true. Hence, a contradiction implies any proposition. Now the second part says, explain why any proposition implies a tautology. Well, we know a tautology is always true, meaning in the truth table, all of the truth values will be true. And we know that true implies true is true. And we also know that false implies true is true. So it doesn't matter what the truth values are for our proposition. If they're true, then they're going to imply the tautology. And if they're false, then they're going to imply the tautology. So hence, any proposition implies a tautology. So let's go back up now and look at question 2, which we skipped, part C and D. So give an example of a proposition other than X that implies X. Well, it should be any contradiction because a contradiction implies any proposition. And we had one very easy to remember example of a contradiction, which was P and not P. We know that a proposition P and its negation can never have the same truth value. So P and not P is a contradiction. Then give an example of a proposition other than X that is implied by X. Well, that should be any tautology. And again, we had an easy to remember example of tautology, P or not P, for the same reason that the proposition P and its negation always have opposite truth values. That means one of them is always true. So P or not P is a tautology. And that answers the question number 2. So we'll end this video here for now, and we'll do some more of propositional logic in the next video.